Hello, and thanks for using TickBoom. In this video, I'm looking at question 7 of the 2001 Extension 1 HSC exam. So this is 7 Part B, which makes it the very final question on that exam. So in theory, the most difficult question of that exam. The reason I'm looking at this is a little while ago, I took a look at the final question of the 2001 Extension 2 exam, and that was largely for a bit of nostalgia. That just happened to be the final question of the most difficult exam in theory that I took when I was doing the HSC. So I thought, in keeping with that theme, why not take a look at the Extension 1 exam, which I also sat in 2001. So this question, being the last question, is meant to be the hardest, and I think in this case it was quite difficult. I can't remember whether it was necessarily the hardest. From memory, I think I managed to work this out. The only reason I guess that is because in the end my official grade for this exam was 99%, and when I look at the HSC raw marks website, where you can kind of go, well, what was the raw mark that you would have had to get that scaled mark, it's also sitting up there in the 98 to 99%. And from memory, I actually think I managed to answer every question on this exam. I do remember very specifically making a silly mistake. I think it was in one of the early questions, actually, question 2 maybe, where I just made a classic mistake that I only realized after the exam, after my math teacher I talked to my math teacher about it and just realized then, I stuffed that up. But apart from that one mistake, I actually do remember doing, or at least tackling all the questions in a sensible way, and I think that played out in the marks. So for that reason, I think I did manage to get this, but now revisiting it almost 20 years later, I did struggle a little to kind of rework out how to tackle this question. It is quite a tricky one, so I think a good one to work through, because at the end of the day it's all about trigonometry, but it requires you to really have a good grasp of a whole bunch of trigonometric ideas. So the way the question reads, we're given this diagram, which you may not notice at first glance, but this is a 3D triangle. So there's actually 4 triangles there. And I'll draw it up to kind of make that clear. But we're told to consider this diagram, and it shows a vertical tower OT of height h meters. There's a fixed point A, and then there's a variable point P that is constrained to move so that the angle AOP is always pi on 3 radians. The angle of elevation of T from A is pi on 4 radians, and we're told to let the angle of elevation of T from P be alpha radians, and then finally to let angle ATP be theta radians. Part 1 says, by considering triangle AOP, show that AP squared equals h squared plus h squared cot squared alpha minus h squared cot alpha. Part 2 says, by finding a second expression for AP squared, deduce that cos theta must be equal to 1 on root 2 sine alpha plus 1 on 2 root 2 cos alpha. And then part 3 says to sketch a graph of theta, where alpha is going to sit between 0 and pi on 2. Identify and classify any turning points and discuss the behavior of theta as alpha goes to 0 and alpha goes to pi on 2. And then that's the end of the paper. So yeah, a lot to this question. To work it out actually does require quite a lot of working. So I'll just get straight into it. So I think the first thing worth doing is to recreate this diagram, and I'll do it in a way that hopefully makes it clear. There's 4 triangles here. It's a 3D diagram. So we've kind of got this vertical that we're told has a height of h, and that goes from point O up to point T. Then we've got this kind of first side triangle. So this is point A here, and that can connect to point T. We're told that's a right angled triangle and that this angle here is pi on 4. That's triangle number 1. We then have another triangle, which this diagram is not going to be perfectly to scale. It won't perfectly replicate the question, but hopefully I can at least do it justice. So we then have this second diagram where this here is point P, and we're told this is also a 90-degree angle, so another right angled triangle, and we're told to call this angle alpha. Then we have the base triangle, so our third triangle is this base of the 3D object, and we're told that this angle here is pi on 3, so that's that angle there. And then finally we have, I might use a different colour, maybe I'll use red or green, say, this kind of final triangle here, the fourth triangle, which kind of represents the outside surface. So this triangle here, if you can imagine this is a 3D triangle, so here's one side, another side, the base, and then this is the last surface. This angle of this triangle, we're told, is theta. And we see that this theta is kind of, in essence, theta and alpha are the core of this question. We're trying to find out things about theta and alpha and their relationship as this point P moves around, because we're told that this point P can move, and if these angles are fixed, how do these two angles change as you move that point P? So that's the essence of the question. Part 1 of the question asked us to show that AP squared, so this line here, squared, is equal to h squared plus h squared cot squared alpha minus h squared cot alpha. And they kind of give us the hint to use the triangle AOP when doing this. So this AOP, that triangle there. Because there's a few triangles you could potentially use here, but for this part we're going to use triangle AOP. Now, hopefully, the rule that we can apply that jumps out to you, hopefully, is the cosine rule, because we've got an angle here, and we're concerned with the length of the line opposite that angle. So, according to the cosine rule, what we can say is that the length of this line, AP squared, is equal to the length of this line, AO squared, plus the length of this other line, the other side of the triangle, so I'll call that PO squared, minus 2 times AO times PO times cos of the angle opposite the side that we're concerned with, so cos pi on 3. So the cosine rule lets us start with that. And since we're concerned with AP squared, it's a natural place to start for this question. But notice what we're trying to ultimately solve to has h all throughout. So what we need to do is get this AO and PO into some function of h. And the way we can do that is to use these other triangles to get this height h into these two side lengths. So first of all, if we use the triangle AOT, what we can say is that the tan of this angle is the opposite over the adjacent, because we're concerned with this. So the tan of pi on 4 is equal to opposite H over adjacent AO. And tan is a good choice here because we're eventually going to get things in terms of cot, and cot is 1 over tan. So I think that's what hopefully leads you to go, well, let's use the tan. I mean, first of all, we want H, and we want the opposite side, and we want the adjacent. So using SOHCAHTOA, hopefully that's where you get to anyway. But it should give you some comfort that we're using tan and we need something with cot eventually. So if I just then rearrange for AO, I can bring the AO over and the tan pi on 4. So we get AO is equal to H divided by tan pi on 4. And that will equal simply H. And that's because tan pi on 4 is equal to 1. And again, hopefully you remember that. But if I just do 180 divided by 4, and then take the tan, we can confirm it with our calculator, which is always a good thing to do in an exam. You don't want to make silly mistakes. You may remember something incorrectly. Always check it with your calculator. So I know AO. Now AO I can just write as H. Now using triangle, we're going to use triangle POT. So POT, and we're going to try and get this side PO in terms of H. So I can use similar technique. Tan of alpha is going to be equal to the opposite, H over the adjacent. So H on PO. So we can just write, therefore PO is equal to H on tan alpha. So bring the PO over here and the tan alpha here. And that's where cot's going to come in, because cot is 1 on tan, so it's H times cot of alpha. So now that we've got AO and PO in terms of H and cot alpha, we can insert them back into this result we got from the cosine rule and hopefully get to what we're being asked to show. So I might just turn over, because I'm running out of space here, but we can now say, therefore, AP squared is equal to AO squared, which will just be H squared, plus PO squared, which will be H squared cot squared alpha, minus 2 times AO, so 2 times H, 2 times H times PO, which is H cot alpha, times cos pi on 3. So that's going to be equal to, I'm not going to factor out my H squared simply because the result doesn't do it. So we're going to get H squared plus H squared cot squared alpha minus 2 H squared cot alpha times cos pi on 3. And we're very close. The only difference is this 2 and this cos pi on 3. But hopefully another result you know is that cos pi on 3 is simply a half. And again, we can test that with our calculator. 180 divided by 3, 60. The cos of that is a half. So this 2 will cancel out with this half. And we get H squared plus H squared cot squared alpha minus H squared cot alpha. And just to double check, H squared plus H squared cot squared alpha minus H squared cot alpha. So that is what we will require to show. So that's part 1. Now I think this was only worth 1 mark, so not too difficult. I mean, quite a lot of work, I guess, for 1 mark, but really we were just using the cosine rule and a bit of SOHCAHTOA. So for the last question of a 3-unit exam, I think that's fair enough. Now for part 2, which is where I think things get a little more interesting. We needed to basically find another expression. So find another expression for AP squared, and then we had to show this result about cos theta. We had to show that cos theta is equal to 1 on root 2 sine alpha plus 1 on 2 root 2 cos alpha. So we've created this relationship between the two unknown angles, theta and alpha. And we're told to do it by finding another expression for AP squared. Now, we've used the triangle AOP in part 1 because we were told to. So the other way we can get AP squared is to use this triangle ATP. Hopefully that kind of jumps out as a natural alternative. So we can use the cosine rule again, just with a different triangle. So, let's use triangle APT, and the cosine rule again. And let's see what we get. So we're going to get AP squared is equal to AT squared plus PT squared minus 2 times AT times PT times cos of the angle opposite, which in this triangle is theta. And that's how we get our cos theta. That's a good sign because we want cos theta. We've got a cos theta using this application of the cosine rule. So happy days, it's a good start. So what I might do is just, before kind of working out AT and PT, I might just rearrange this for cos theta. So we can write, I'll bring this over and this over, so we'll get 2AT PT cos theta is equal to AT squared plus PT squared minus AP squared. That's, I've just moved this over and then this over. So if I isolate cos theta, that's going to be AT squared plus PT squared minus AP squared divided by 2 times AT times PT. So that's now we need to simplify this to kind of eventually, hopefully, get it into this format, the 1 on root 2 sine alpha plus 1 on 2 root 2 cos alpha. So similar to what we did before, we can use these side triangles to then get the side that, the two sides that we need. The good news is these are both right-angled triangles, so now we can use Pythagoras and kind of get those lengths pretty easily. So first I'll focus on AT. So if we use triangle AOT, what we can say is that this hypotenuse, AT squared, is equal to AO squared plus TO squared. So that's just using Pythagoras. Now what is AO squared? If we come and look at what we are working in part 1, AO is H. So that's going to be equal to H squared. And what's TO squared? Well, TO we're told is H. So that's also H squared. So we can write AT squared as 2H squared. So we can write AT as the square root of 2 times H. And getting this square root of 2 is a good sign because we've got square roots of 2 in our result that we're working towards. So that's a good sign. So that's AT. Now let's do a similar thing to get to our PT. So here I think we should use triangle POT. So we'll use triangle POT and we will say that PT squared is PO squared plus TO squared. So PT squared is equal to PO squared plus TO squared. Once again, that's thanks to Pythagoras. PO squared, if we come back to part 1, was, well, PO was H cot alpha. So PO squared will be H squared cot squared alpha. So H squared cot squared alpha, and TO squared is just our H squared. We were told the height of TO. So if I kind of just factor this out, maybe I've got one more line before I have to turn over. So that'll be H squared cot squared alpha plus 1. And I'll just turn over and continue this. So we're focused on PT squared, and we've got H squared. Now cot squared alpha plus 1, hopefully you know the result that that's cosec squared alpha. So there's a result cosec squared alpha, or cosec squared x at any angle, is equal to cot squared x plus 1. So if I've got cot squared alpha plus 1, I can write that as cosec squared alpha. So PT squared is equal to H squared cosec squared alpha. So I can take the square root of both sides and get PT is equal to H cosec alpha. So now that we've done that work, we've got our cos theta in terms of AT and PT and AP. We've got our AT, we've got our PT, and we also got AP squared from part 1. So this is where part 1 and part 2 link together. So now we can insert everything, and hopefully when we simplify, we get to this result. So let's give that a try. So what we can say is that cos theta is equal to, and let's start putting in our results. So AT squared, so that's going to be 2H squared plus PT squared, which is going to be H squared cosec squared alpha, minus AP squared, which from part 1 we can insert. So it will be minus, and I'll put it all in brackets, H squared plus H squared. Actually, at this point it might be worth factorizing the H squared out. So let's just do that. So it'll be minus H squared times 1 plus cot squared alpha, or I might say cot squared alpha plus 1 minus cot alpha. Hopefully you see this is why I thought it worth factorizing out the H squared. So we can throw in a cosec squared and start to cancel some things out. And that's all divided by our denominator is 2 times AT, so 2 root 2H. So 2 root 2H times PT, which is H cosec alpha. So that's what we need to simplify. It kind of at first glance looks a bit complex, but let's see. Hopefully things fall out. So we can then say, let's get this expanded. So we'll go 2H squared plus H squared cosec squared alpha minus H squared, and this part if I just take that as one thing, is cosec squared alpha minus h squared cot alpha. So that's the numerator, and the denominator is simply 2 root 2 h squared cosec alpha. Now this plus h squared cosec alpha and minus h squared cosec alpha cancel, which is good. There's a h squared, in the terms that remain, there's a h squared in both, and there's a h squared here. So actually all of those h squareds also cancel. And so what we're left with is 2 minus cot alpha over 2 root 2 cosec alpha. So a lot of that complexity did disappear. I guess now the question is, how do we simplify this? And I think we need to go to our definitions of cot and cosec. So we know cot alpha is simply equal to cos alpha on sine alpha, because cot is 1 on tan and tan is sine on cos. So that's cot alpha, and then cosec alpha is equal to 1 on sine alpha. So let's see what we get when we insert those. So we'll go, I'll just write this 1 on 2 root 2 out the front times 2 minus cos alpha on sine alpha, all divided by 1 on sine alpha. So that's going to be 1 on 2 root 2 times, and I'll get this common denominator, so it will be 2 sine alpha minus cos alpha all on sine alpha. So that's this numerator here. And dividing by 1 on sine alpha is the same as multiplying by sine alpha. That means those two sine alphas disappear. And now I can multiply this 1 on 2 root 2 through. So we'll get 2 sine alpha on 2 root 2 minus cos alpha on 2 root 2. These 2's will cancel in front of the sine alpha. And that then leaves me with 1 on root 2 sine alpha minus 1 on 2 root 2 cos alpha. And if I come back to the expression, that is exactly the expression that we had to show. So that's as required. So that is part 2 done. So quite a bit to it. I can see why this bit was worth a few more marks. I mean, we're kind of starting with our cosine rule again and getting our Pythagoras results to get the other sides. But I suppose where the extra marks were awarded was having the ability to simplify what at first glance looked like quite a convoluted result. So that said, I think as long as you know your definitions of all your different trigonometric identities, I actually think the simplification actually turned out to be not too bad. So really this was more a test of a student's ability to just kind of methodically tackle a question and not kind of be so daunted by something as to not even try, which maybe a lot of students would. They might see something like this and maybe they're running short on time because it's the last question of the exam and they just kind of abandon it. That's possible, but hopefully you kind of, with enough ability, I guess, to stay calm, you can kind of see how this isn't too bad at all. So that brings us to part 3, which I might just turn over for part 3, because we're asked in this part to sketch a diagram of theta for the domain 0, alpha between 0 and pi on 2. So we're told to sketch that and also do a few other things. We're told to identify and classify turning points, any turning points. So by classifying, it's basically, is it a local minimum or local maximum? And then the other thing we're asked to do is to discuss theta, what theta would be as alpha tends towards 0 and as alpha tends towards pi on 2. So basically the two extremities of this domain, because this domain is not inclusive. So we're kind of asked to draw it within these 2 points but not including them, and then told, well, effectively what are those 2 points? What would theta be at those 2 points? So I guess naturally the first thing to do is to draw up an axis. So that's why I thought a new page would be a good idea to have enough room. So really, if I just label these axes, we'll have alpha and theta and our origin. Now we're concerned with alpha between 0 and pi on 2, so I'll call this pi on 2, so this is pi on 4. So really that's the domain we're concerned with, so I'll just draw a dashed line here to indicate that. And we're not actually including pi on 2, that's not kind of in the domain, but effectively we will want to know what are those points. And so maybe here I'll call that a half, and I'll call that 1, and I'll call that 1.5. So yeah, this task is to sketch theta. Now in the prior part of the question, we worked out cos theta, and I think that's going to come in handy. But fundamentally we need to isolate theta and then differentiate it so that we can get our turning points. But I think before I go down that path, before I go about doing that step of isolating theta and differentiating it, I think this part here is worth doing first, because it actually falls out of this result we just proved. And the beauty of this question is it asked us to prove this result, and it told us this is the result to prove, so that even if you can't work it out, even if you couldn't get there, you can still rely on it for part 3 and hopefully pick up some marks. So what we can say right away is from part 2, we know that cos theta is equal to 1 on root 2 sine alpha plus 1 on 2 root 2. Let me just double check that. Oops. Maybe I've got this wrong. I've just noticed I've made a very rookie error of forgetting about double negatives. So that's a negative and that's a negative, which means this would have been a plus, which means this would have been a plus, which means this would have been a plus, and this would have been a plus, and this. And that is what we were asked to prove. Yes, there was a plus there, so actually I hadn't noticed, but I actually made a mistake there, but thankfully I've just spotted it, because yeah, that didn't look like what we were ultimately asked to show. So good news that I fixed that up. So this is what we've just shown. So that's plus 1 on root 2 sine alpha plus 1 on 2 root 2 cos alpha. We know that from part 2. So if I isolate theta here, theta is equal to the inverse cos of that plus 1 on 2 root 2 cos alpha. So now we can just go, well, when I plug in 0 here, what does theta become? And when I plug in pi on 2 here, what does theta become? And that that's then this part done. We can kind of get those marks and also plot those points so that we can see the basic options for what it might look like in between. So when alpha is equal to 0, theta would be equal to the inverse cos of 1 on root 2 sine 0 plus 1 on 2 root 2 cos 0. So that's going to be the inverse cos of simply 1 on 2 root 2. And the reason is because sine of 0 equals 0 and cos of 0 equals 1. And again, in an exam, you might always want to check these things. So 0 sine is 0 and cos of 0 is 1. So that's why this disappears and this just becomes 1. So if I then plug that into my calculator to try and get it as a value, so we'll have square root of 2 times 2, take the inverse, and then take the inverse cos. So it's 69.295188895 and so on degrees. And then to get that in radians, I divide by 180 and multiply by pi. I'll use 22 on 7 as an approximation of pi. And so I'll go divided by 180 times 22 divided by 7. And I'll get 1.209915997. So about 1.21 is where we plot this. So this would be 1.25. So somewhere in that vicinity. So as alpha tends towards 0, theta tends towards the inverse cos of 1 on 2 root 2. And that's kind of that part. Discuss theta as alpha goes to 0. Well, it tends towards 1 on 2 root, the inverse cos of 1 on 2 root 2. Now what we want to do is, I'll have to turn over, but we'll say when alpha equals pi on 2, theta equals the inverse cos of 1 on root 2 sine pi on 2 plus 1 on 2 root 2 cos pi on 2. Now again, you probably could remember these, but sine 90 is just 1 and cos 90 we'll see is 0. So that means this cancels out. This is 1, so we get cos, the inverse cos of 1 on root 2, since sine pi on 2 is equal to 1 and cos pi on 2 is equal to 0. So again, if we plug this into our calculator, we'll take square root of 2, take the inverse cosine of that is 45 degrees, and then divided by 180 times 22 on 7 to get into radians, times 22 divided by 7 is 0.7857142886. So if we come back to our chart, that's what we want to plot here, about 0.78. So if this is 0.5, this would be 0.75, so it's kind of here, it's in this vicinity. So again, in terms of discussing theta, as alpha approaches pi on 2, theta approaches this inverse cos of 1 on root 2. And so you kind of just need to identify that. So this is the inverse cos of 1 on root 2. And this is the inverse cos of 1 on 2 root 2. And so that's what theta is tending towards. Now the question that remains is, does the chart look like this? Or does the chart look like this? or is it a straight line? What happens in between these two extremities of our domain? And that's where identifying and classifying the turning points becomes key. So we need to now do the work of this point here. That will help us finish our sketch, and then that will be this part of the question done. So, where to begin here? Now, I think we actually can't rely on this form of theta that we've just used from part 2. We actually need a new form of theta that's a bit simpler to differentiate, because we need to differentiate this. And so I think what we can do is we can kind of rewrite that result in a new form. So we can let this 1 on root 2 sine alpha plus the 1 on 2 root 2 cos alpha, let's say that's equivalent to some r cos alpha minus beta. So essentially we just want to take this sine and cos and say, well, what angle and I guess magnitude or kind of value r would be equivalent to this whole thing. So if I can find r and I can find beta, I'll then have a kind of cos theta in this new form that hopefully is easy to differentiate. So essentially cos alpha minus beta, hopefully you know we can write as cos alpha cos negative beta minus sine alpha sine negative beta. That's the expansion of cos a plus b. So using the fact that cos is even and sine is odd, you could say that's r cos alpha cos beta, since cos negative beta is cos beta, plus sine alpha sine beta, since sine negative beta is negative sine beta. And here I haven't forgotten to do the double negative, so hopefully we can carry on there without letting a mistake run through. So I'll just expand that. So we'll get, and I'll write this, maybe I'll write this in the same order as this. So we'll get r sine beta times sine alpha plus r cos beta times cos alpha. And now what we can do is equate what's in front of the sine alpha on both sides and what's in front of the cos alpha on both sides. So what we can say is that for these two sides to be equivalent, what that means is r sine beta would have to be equal to 1 on root 2, and r cos beta would have to be equal to 1 on 2 root 2. That's what would be required for these two things to be equivalent. So now what we need to do is kind of solve for r and solve for beta, and then plug those back in, and then isolate theta, because remember this is equal to cos theta, which means this would be equal to cos theta. So then we take the inverse cos of whatever we end up with. So I think what we can do is square both sides. So we'll get r squared sine squared beta equals 1 on 2. And r squared cos squared beta equals 1 on 2 squared is 4 times 2 is 8. And the reason we want to do that is so that we can add it up. So we'll get r squared sine squared beta plus r squared cos squared beta would equal 1 on 2 plus 1 on 8, which means r squared sine squared beta plus cos squared beta equals, this will be 4 on 8, so 5 on 8. Hopefully you know that sine squared beta plus cos squared beta is 1, so that means r squared is equal to 5 on 8, since in general sine squared x plus cos squared x is equal to 1. So r would be the positive square root of 5 on 8. So that's the r part solved for. So now we need to think, how do we solve for the beta, and then we can plug that bit in. Now, I think where we can start, I might have to turn over, but we can say that tan of beta, by definition, would be sine beta on cos beta. And notice that we have a sine beta and a cos beta here. We just have them both multiplied by r. So why not just multiply top and bottom by r? Because we haven't changed anything. So now I know that r sine beta is 1 on root 2. And I know that r cos beta is 1 on 2 root 2. So that's going to be 1 on root 2 times 2 root 2. These cancel, so we just get 2. So that means our beta is equal to the inverse tan of 2. Alright, so now what I can do is I can come back and say cos theta is equal to, we proved that cos theta was equal to this, and we've just proved this is equal to root 5 on 8 times cos alpha minus tan to the minus 1 of 2. So I can then isolate theta. So theta would be equal to the inverse cos of root 5 on 8 cos alpha minus tan to the minus 1, 2. And that looks like a scary proposition, but actually, as we'll see, differentiating this is relatively easy compared to differentiating this. So let's do it. So in terms of differentiating this, we're going to use the chain rule because we've got a function of something. So we kind of need to differentiate the outside and differentiate the inside. So it would be handy to know that the derivative of the inverse cos of something, that is equal to, and again this is a result you probably need to know, negative 1 on the square root of 1 minus x squared. And it would probably be a totally separate question to be asked to prove that, but I think you could take that as given, and it's not like a marker would be expecting you to prove that. The other derivative that's worth knowing is that the derivative of what's on the inside, cos x, is simply equal to the negative of sine x. So I think with those two results at the front of our mind, we can say that theta dash, the derivative of this, will be, let's differentiate the outside. So we'll take negative 1 divided by the square root of 1 minus what's on the inside squared. So 1 minus root 5 on 8 cos alpha minus tan to the minus 1, 2. All of that squared. It's the square root of all of that. Negative 1 on that. Times, and then the derivative of the inside. So the root 5 on 8 will just kind of come out, since that's not a function of x, times negative sine of what's on the inside, alpha minus inverse tan of 2. Now that at first glance looks like a total nightmare, but as we'll see, it's actually not too bad to deal with. So these two negatives cancel. Good thing to notice now rather than later. So so we just get a root 5 on 8 divided by this kind of beastly looking thing here, 1 minus root 5 on 8 cos alpha minus tan to the minus 1, 2, all of that squared, times sine alpha minus 10 to the minus 1, 2. Alright, that is the derivative. Now, we're concerned with the turning point. The reason we're doing this is simply so we can identify and classify any turning points that exist in this range. So fundamentally, all we want to do now is set this equal to 0. When is theta dash equal to 0? And the beauty of that, it means that this whole thing just disappears because we multiply it up and we get 0. So actually theta will equal 0 when sine alpha minus 10 to the minus 1, 2 is equal to 0. Because this whole thing, when we set it to 0, means we can multiply it up and it disappears. Now, when is sine 0? Well, we know that sine of 0 equals 0. We even saw that earlier somewhere. I think we relied on that. Yeah, here. So sine 0 is equal to 0. So that means this will be 0 when what's in here is 0. Or in other words, alpha is equal to tan minus 1, 2. That is where our turning point occurs. So even though this derivative looked like a real monster, the thing that we needed from it popped out quite easily. Okay, so alpha equals 10 to the minus 1 on 2. I'll have to turn over. But when alpha equals 10 to the minus 1, 2, what does theta equal? Well, theta will equal, I think we should use this result here. So cos to the minus 1 of root 5 on 8 cos alpha minus 10 to the minus 1, 2. Alpha is 10 to the minus 1, 2. So 10 to the minus 1, 2 minus 10 to the minus 1, 2. So that's cos to the minus 1 of root 5 on 8 cos of 0. Now, we've already thought about what cos 0 is. Cos 0 is equal to 1, as hopefully we know. So this just becomes 1, so it's equal to cos to the minus 1 of root 5 on 8. So therefore, we have a stationary point, or a turning point, stationary point at the point tan to the minus 1, 2, comma, cos to the minus 1 root 5 on 8. So that's kind of identifying the turning point. Now we have to classify it. Is it a local minimum or is it a local maximum? And for that, we need to do some calculations. Does theta, if we take alpha a value a little bit smaller and a little bit bigger, what does theta look like? So actually, I should probably calculate this. So at alpha equals 10 to the minus 1, 2, theta is equal to, so we'll just get our calculator, 5 divided by 8, the square root of that, then the inverse cos, so it's 37.76124391 degrees, divided by 180 times 22 on 7 would give us, divided by 180 times 22 divided by 7, 0.6593233306 radians. So what do we get at alpha equals 10 to the minus 1, 2 minus some small number? Let's call it 0.1. What would theta be? So theta would be cos to the minus 1 of root 5 on 8 cos, in this case, tan to the minus 1, 2 minus 0.1 minus tan to minus 1, 2. So that's going to be the inverse cos of root 5 on 8 times cos of negative 0.1, which will be, and let's just plug that into our calculator. So 0.1 negative, the cosine of that, actually I'll start 5 divided by 8, the square root. Let's store that. And then we'll go 0.1 negative, the cos of that. Let's store that. Now multiply. And take the inverse cos of that. So that's 37.761356557 degrees divided by 180 times 22 on 7 divided by 180 times 22 divided by 7. So that's 0.65932527.3. 0.659325 instead of 23. So this is higher, slightly higher. So when we move back slightly, when we move alpha, make it a little bit smaller, we get a slightly higher number. What happens when we make alpha slightly bigger? So at alpha equals 10 to the minus 1, inverse tan plus 0.1, theta would be, if I just follow this pattern, it'll be the inverse cos of root 5 on 8 cos of plus 0.1 this time. So let's just do that. Now I think I've already got the square root of 5 on 8 stored. So now I just need 0.1, the cosine of that. I'll store that. So recall 1 times recall 2. Take the inverse cosine. We get 37.761356557 degrees, which is identical. But just for completeness, I'll finish off the math. Divide by 180 times 22 divided by 7. 0.65932527.3, which is the exact same number, so also higher. So what we can conclude is that at alpha equal tan, inverse tan of 2, that's a local minimum because on either side theta is higher. So therefore the turning point inverse tan of 2 inverse cosine of root 5 on 8, that is a local minimum. So I think that's the key. That's what we've identified the turning point, we've classified it. Now we can go back to our chart and plot it, and I think that will be this question done. So our chart was all the way back here. It involved quite a bit of work. So what was our alpha? It was the inverse, we'd take the inverse tan. So 63 degrees. So this is 90 degrees, this is 45. So 63 is kind of falling somewhere around here. And the inverse cosine of root 5 on 8. So 5 divided by 8, square root, inverse cosine, divided by 180 times 22 divided by 7. Don't know why I did that, because I could have just looked it up here. Anyway, 0.659 and so on. So that's 0.5. That would be 0.75. So it's going to be, somewhere around here. It's not perfect, but what we know is that this is what the curve looks like in this domain. So we've done it. We've sketched theta for alpha in this domain. We've identified and classified our turning point so that we knew it was a local minimum, so that we knew to draw it like this. And we've thought about theta as alpha goes to 0, theta goes to the inverse cos of 1 on 2 root 2, and as alpha goes to pi on 2, theta goes to the inverse cos of 1 on root 2. So that's that question done. We've done each of these three things that were asked of us. So there you have it. Quite an involved question in the end. I mean, if I come and look at what we've just had to do. So we've started with this diagram, this 3D triangle, which already might be a bit off-putting to some, especially given it's the last question, so you're probably already quite fatigued from everything else you've worked through. But as long as you kind of don't balk at the seemingly complex diagram, I think you can pick up marks in part 1. It was just applying the cosine rule. Arguably part 2 was just applying the same rule, just for a different part of the triangle. I suppose you had to realise this was a 3D diagram, and this triangle here, like there's basically two ways to get AP squared. I think maybe that's why part 2 is worth more marks. And then I think all the hard work came in part 3, because we had to kind of use our result in part 2 and think about that, but then also find another form for theta so that we could then differentiate it and get the turning point. So yeah, that was quite involved. That did require quite a lot of work, which is why it was worth so many marks. But yeah, hopefully having now worked through all that, that all made sense. Clearly to answer this, you had to have a very comprehensive knowledge of trigonometry. A whole bunch of results that we've been using, from sine and cos, tan, sine squared x plus cos squared x, knowing that things like cot and cosec, you know, we really had to use quite a lot, that cot squared x plus 1 is cosec. So yeah, quite a hard question in the end. I think worthy of a final question on an Extension 2 exam. I think that's probably fair to say. So yeah, hopefully you found all that helpful, and tick boom.